Okay, lesson 5. This is a pretty long one, so I'm going to try and go quickly through it. You probably should pause at certain points and try and graph it yourself and see what happens. Desmos might be faster than using your graphing calculator, but whatever you have should work just fine. So this lesson we're doing the stretches. We're doing the A value and the B value, so both vertical and horizontal stretches, and we're going to see how they work. So the graph of f of x equals root of 4 minus x squared is shown. It's a half circle. Write the equation where you have an a value of 3, so multiplying by 3 by the outside. So that's going to be f3 times f of x is equal to 3 root 4 minus x squared. Use the graphing calculator to sketch this. You could, if you want to use Desmos, I would put maybe an A instead where the 3 is, and then you can create a slider and you can see how all of them work, and that would do for the whole page. But this is going to be a vertical stretch. It actually starts there, and it's going to stretch up 3 times as high. So that's 2, 4, 6, goes up to there. So a very tall half oval. Describe how the number 3 affects the general sketch y equals f of x. So this is a vertical stretch by a factor of 3. All the y values are being multiplied by 3. So we always use the word factor. That just means multiply everything by 3. It didn't affect the two ones that have a y value of 0. Multiplying by 3, they stay 0. The x-intercepts of the graph they stay the same. Because multiplying by a certain value on the x-intercepts don't do anything. The y-intercept, it goes from 0, 2, and it transforms into 0, 6. Because it comes 3 times as big. Good, part 2. Now what happens if we did it as a half of f of x? Write the equation. Well, f of x, 1/2, is equal to 1/2 root 4 minus x squared. And that's going to look like this. It's a little tiny semicircle. Again, if I were you guys, I would probably plug this into Desmos and I would put an a value in front of the equation, and then you can create a slider and you can quickly see how it's going to manipulate it. Describe how the number half affects it. So this is, again, we call all of them stretches technically, but we sometimes use the word we call them all stretches, but sometimes we use the word compression if it's going to be actually shrinking it. So this is a vertical compression by a factor. So the factor is just whatever you're multiplying all the values by, and this one's by a half. By a factor of a half. What happens to the x-intercepts? No, they're the same. What happens to the y-intercept? It goes from 0, 2 to half that, which is 0, 1. Complete the following statements using the results from part 1 and part 2. So compared to the graph y equals f of x, the graph, if you add an a value, what does the a do? So the a results in a vertical stretch about the x-axis. It's stretching it relative to the x-axis, basically. The further you are from the x-axis, the more you're going to be stretched. And if you're on the x-axis, you don't get affected by a factor of a. Sometimes we use the absolute value of a here because we treat the negative part of it as kind of a separate thing. If we replace y with 1 over ay, so this is the same thing, just seeing it on the other side, then y equals f of x becomes 1 over a, y equals f of x, which gives us our thing. So all of these, if we wanted to see them in replacement notation, is going to be flipped upside down. So if you have a stretch of 3 in the first part, it's going to be replace y with 1/3 of y. Moving on, now our b values. So exact same function. So hopefully you have these things saved in your calculator or in Desmos, so we can do it nice and quick. Now what happens if we replace it with f of 4x? So in our function, f of 4x is going to equal the root of 4 minus bracket 4x all squared. And that will simplify to the square root of 4 minus, you square both parts, so it should be 16x squared. All under the root. And what does that one look like? When you graph it, it actually is a horizontal compression. This is at 2, so this one comes into 1. Sorry, a quarter, a half. It's a quarter of its original value, so it goes to a half. And the y-intercept's the same. So a really tight graph. Describe how the number 4 affects the general sketch y equals f of x. This is a horizontal compression. Compression, even though it's stretched, all of them, we say stretch works both ways. Sometimes we say expansion or compression are the more specific ones. By a factor of a quarter. So all the x values are being multiplied by a quarter in this one, which is backwards to how it looks, because it's inside the function, so it's going to be backwards. What happens to the x-intercepts? Well, they go from -2, 0 to -0.5, 0, and from 2, 0 to 1/2, 0. So they shrink. What happens to the y-intercept? It stays the same. So we're going to have invariant points. The b value will leave all the y-intercepts as invariant points. Part B. Now what if you had a b value of 1/3? What does that look like in the equation? So f of 1/3 x is equal to root 4 minus 1/3 x all squared. And when you expand that, again you square both parts. This one is 1/3 squared becomes 1/9. So root of 4 minus 1/9 x squared. Graphing that one, it actually multiplies everything by 3. So this starts at 2, so it goes to 4, goes to 6. This one goes to -6, and this one stays the same. And then we draw a nice little, really wide semi-oval. Okay, so once again, you could use Desmos and you could put an a value in brackets in where the x is, or a b value is probably better, and create a slider and see how that affects it if you want to do more than just 4 and 1/3. And you can see all the transformations. Describe how the number 1/3 affects it. Well, this is a vertical stretch, horizontal stretch. By a factor of 3. Everything's being multiplied by 3 horizontally, all the x values. What happens to the x-intercepts? They go from plus and minus 2, 0, to plus and minus 6, 0. They'd be multiplied by 3. Complete the following. What happens to the y-intercept? Same. It's the same in the original function, not the same as multiplied by 3. Complete the following statements. Compared to the graph f of x, if you have a b value, what does the b do? It results in a horizontal stretch about the y-axis. So it's all being stretched away from the y-axis. That's kind of our point of our anchorage, we might say, because there's a lot of ways to stretch something. Basically, like what's holding still and what are you pulling on. So you anchor it at the y-axis and you pull it from both sides. By a factor of 1 over b. So this one is backwards, unlike the a value. The a value is the right way around. This one's backwards. You have to actually flip it. So fractions become a stretch, and whole numbers become a compression. And then we've got the replacement notation. You can replace x with b of x. Okay. So a little bit more complicated of a function this time. Let's see if we can do a couple transformations on a more complicated function. This is our function. Now we want to do it with an a value of -3. So let's replace that first. Is equal to -3 on the outside, x cubed minus 2x squared minus 5x plus 6. And we can expand that out by doing our rainbowing. So it's -3x cubed plus 6x squared plus 15x. -3 times 6, 6, 12, 18, minus 18. So that's our new function, and then we want to graph that. And we should be able to do it without the graphing calculator if we know that this is a vertical stretch and a flip. Actually, it's two different things. So let's pick out a couple key points here. I'm going to do, we could do the y-intercept, we could do the x-intercepts. I really should have another color. Let me see if I can grab one. Alright, hopefully this will make it a bit easier to see. Got red. So we're going to pick out that point, we're going to pick out that point, we're going to pick out that point, we're going to pick out this point, and if we wanted to, we could pick out the vertices as well. Let's actually do that. That point and that point, because they're pretty easy to find. So we're going to take all these things and we're going to stretch them by multiplying them all by -3, their y values. So this one stays the same, this one stays the same, and this one stays the same. Let's find out where the two vertices go. So this is 4, that's 5, 6, 7, 8. So multiply by 3, 8, 16, 24, and multiply by -1, flips it upside down. So this actually goes down to -24. This one right here is at -4, so 4, 8, 12, it goes up to +12. Let's throw on the y-intercept as well, just for fun, so we can connect it a little bit better. And that one's at 6, so 6, 12, 18, down to -18. Okay, now we need to connect all these dots. Not this guy and this guy, but we need this guy and all these intercepts. So it should come up, then down, through that intercept, back, and then it shoots off. And this one shoots off. So that should be our new function. I could have made that a little bit rounder, but it's only an estimate. We've got a couple key points on there, and that's pretty good. Use a graphing calculator. Well, we've sketched it. Describe the number -3, how it affects the general sketch. If you're using a graphing calculator, you need to change the window, probably. So you're going to want the window to be, for x, -5 to +5. For y, from -25 to +25. To be able to see it correctly. So you have to go into window and change those settings. Describe how it affects it. So this is a vertical stretch. By a factor of 3. So this is what I said about the absolute value thing. We actually always break this down if we're describing it into two parts. We treat the negative part of it as its own thing. So the vertical stretch is just the absolute value of A in this case, which is 3. So we're stretching all of our points by 3. So that's 1 point, and then we have a second point, which is a reflection. And then we also reflect in the x-axis. I know a lot of people want to write it's a vertical stretch by a factor of -3, but we just never say it like that. It's not technically true. You're not stretching it by a factor of -3. Stretching it by a factor of 3, that's usually an amplitude, so it's an absolute value, and then reflect is its own thing. Okay, what happens to the x-intercepts? Well, they still stay the same. What happens to the y-intercepts? What were our y-intercepts? We only had one. It was at 6. So we went from 0, 6 to 0, -18. Good. Complete the following statement compared to the graph f of x. If you add an a value where a is less than 0, so when a is negative, what happens? This results in a vertical stretch about the x-axis, so it's stretching it from the x-axis, that's what you're pulling it from, by a factor of the absolute value of a. So when we're talking about absolute value of a, we usually mean that as an amplitude. So basically it's just how much are you stretching it irregardless of direction. And then also a reflection in the x-axis, so two different things. Good. We're going to do the same thing with b now, exact same function. This time we're going to replace it with -1/3 x, so it's going to have the two things again. Write an equation for it. So this actually takes a little bit of a time. F of -1/3 x is equal to -1/3 x all cubed minus 2 times -1/3 x all squared minus 5 times -1/3 x plus 6. And yes, we have to unfortunately expand that, but I'll do that nice and quick for you guys. So 1/3 to the power of 3 is going to be 1/27th, I believe. Let me make sure I get all the right numbers. Yeah, and negative cubed is still negative, so -1/27th x cubed. This is going to be positive, so it's still negative. -2 over 3 squared is 9, x squared. Minus, so plus 5/3 x plus 6. So there's our function. Now we need to graph it. So we have one anchor point, which is the y-intercept. That guy's not going to move at all. But now all of our x values are going to be affected. So all of our x values, why don't we pick a couple points here? We can do the intercepts. 1, 2, 3 of them, and let's do the vertices as well. 1, 2 of those. So we got 1, 2, 3, 4, 5 points to transform. So this guy was at -2. This is a third, so we're actually expanding it. We're multiplying it by 3 and then multiplying it by -1. So -2 times -3 is going to be +6. That guy goes way over here. So it both flips and expands. You can, of course, graph this to look at it. This is close to -1. So that's going to move to +3, so just less than +3. Somewhere over here. This guy is 1, so he goes over to -3. This guy is 3, so he goes to -9. And this guy down here is 2, so he goes to -6. The heights of them are not affected. We're not changing the y values, we're only changing the x values. And then we connect these dots as nicely as we can. So I'm going here, to here, to here, to here. it keeps going down. Make sure you throw arrows on the end of it when you're doing these sketches. This graph continues. And do be mindful of the end. Most people are pretty good at drawing their points on, but then sometimes people will like draw it going up when the graph didn't say it was going to go back up or anything. So be mindful which way the arrows are actually going. They do have to kind of give you an impression of where the graph is going to continue to go. So, describe what negative a third does to the graph. Well, this is again 2 points. The first one is a horizontal stretch. By a factor of 3. Horizontal stretch by a factor of 3. Remember, all the ones inside the function are backwards. What was it? H value was backwards in terms of if it was negative, it's positive. If it was positive, it's negative. The B value is backwards in terms of if it's divide, it's multiply. And if it's multiply, it's divide. So basically, you have to flip it every single time. So a third becomes 3. So we are stretching it by 3, and then we're also reflecting it in the y-axis. So 2 different things. What happens to the x-intercepts? We had 3 of them this time, so we actually have to do a bit of a graph. So it goes from -2, 0, 1, 0, and 3, 0. This became 6, 0, this became -3, 0, and this became -9, 0. So all the x values multiplied by -3. The y-intercept stayed the same. So compared to the graph f of x, if you have a b value where the b is negative, we're going to be doing 2 different things. This results in a horizontal stretch about the y-axis, so stretched from the y-axis, pulled from both sides, by a factor of 1 over absolute value of b. So when you're talking about the stretch, first you have to flip the b because you know it's backwards, and you have to ignore the negative part of it. That's what that means. So if it was -3, it has to be a factor of a third. Ignore the negative, but then you say the negative out here, and it's also reflected in the y-axis. 2 different things. Even though when you go here, you kind of do it all in one step. It's weird, it's just kind of a language thing. Okay, nice little summary page. This is actually a great page. This is going to be a page you're going to want to look at and make sure you have memorized before the test. So, a and b values. If a is between 0 and 1, the graph of f of x will be stretched vertically by a factor of a about the x-axis. So even though it says stretched, it's going to be multiplied by a. This is actually going to be a compression. So some people call this a compression. I don't mind either way. I think saying compression is a little bit nicer, but when you say by a factor of, it's always the same value. So in this case, it might be like a third. So you could say it's vertically stretched by a factor of a third, or you could say it's vertically compressed by a factor of a third. Doesn't matter either way. And that's what it says up here. It says stretch is the general term that implies both expanding or contracting, or you could use the words expansion or compression more specifically. Doesn't matter. If a is bigger than 1, so this is stretched vertically by a factor of a about the stretched about the x-axis. So I always have to visualize it. So the exact same words here. And we don't use absolute value a just because it's not negative, so it doesn't really matter. But really, you could put absolute value a. It doesn't really hurt it. If a is negative, the graph will be reflected in the x-axis and then stretched vertically about the x-axis. So two different things. It doesn't say by a factor of a, but multiply by the absolute value of a for the stretch as well. Okay, b values, almost the same thing here. If the b value is between 0 and 1, this time it actually does expand because you have to flip it. So this is stretched horizontally by a factor of b about the y-axis. So this one's actually our expand. If b is greater than 1, this is actually our contraction. So it is stretched horizontally. Might want to say compressed. By a factor of b about the y-axis. Again. So they're opposite, right? In this one, when a is big, it's a stretch. When b is small, it's a stretch. And when b is big, it's actually a compression. There's as many numbers between 0 and 1 as there are numbers above 1, kind of in one sense, because there's infinite of both. So it's not like you're limited in terms of numbers by being between 0 and 1. There's many, many numbers in there. When b is negative, it's reflected in the y-axis and stretched horizontally about the y-axis by the b factor again. Okay. Everything on this page is just a summary of what we just said. There's kind of a nice little memorization box here. When a is big, it's a stretch. When a is less than 0, it's a stretch and a reflection. When b is positive, it's a stretch. When b is negative, it's a stretch and a reflection. So let's try some examples. Write the replacement for x or y, and write the equation for the image after each transformation. So a horizontal stretch by a factor of 6 about the y-axis. Horizontal stretch by a factor of 6. So this is going to be y is equal to f. This is going to be inside, and it's got to be backwards, so it's got to be 1/6 of x. Let's get this in. Yeah, I'll write the replacement. So we're replacing x with 1/6 of x is the replacement formula, and it ends up with that formula. A vertical stretch by a factor of 1/5. So vertical stretch, we're replacing y with, you have to actually flip it, we're replacing it with 5y. That's why I don't like that thing, because it's always backwards. But then when it gets to the formula, it's going to be the right way around. So y equals 1/5 f of x. Because to move it to the other side, you're going to divide by 5. Okay, so it might take some practice to make sure you get that comfortable with that. A reflection in the x-axis. So a reflection this way, which is going to be a y negative. And a vertical stretch about the x-axis as well by a factor of 3. So basically we're going to take y and we're going to place it with stretch by a factor of 3, so negative 1/3 y. We have to flip it there, but then when it goes to the function, it's negative 3f of x. Good. A horizontal stretch about the y-axis by a factor of 1/2. And a vertical stretch about the x-axis by a factor of 1/4. So x is going to be replaced with 1/2 x, and y is going to be replaced with 4y. So it has to be backwards here, and then it goes normal in the formula. So the actual formula is 1/4 f of 1/2 x. Oh, sorry, this is backwards. Yeah, sorry, I did this one mistake. I did it right there. I did it right there. I did it right there. This was backwards, though. If it's a horizontal stretch by a factor of 1/2, that means it's going to be a 2. Here, both of these are backwards. I forgot I did it correct there. It was 6, so it became a 1/6. Here it's 2, so it becomes 2x. Sorry, one mistake. So 1/4 f of 2x. Good. Last page finally. How does the graph of 3y equal f of x compare to the original graph? I turn it into the original thing, the other side, so it's actually 1/3 f of x. So this is an a value of 1/3. So this is a vertical stretch. I'm actually going to write compression. It's a vertical compression by a factor of 1/3. So hopefully some of these questions are nice and easy. What happens to the graph if you make these changes? If you replace x with 4x, well, that's going to actually horizontally compress it because it's backwards. So this is a horizontal, if you want to see it in the function notation, it's f of 4x. This is a horizontal compression by a factor of 4 or 1/4. Sorry. You always say what you multiply the values by, even though you have the compression there. So multiply everything by 1/4. If you replaced y with 1/3 y, so that's the opposite of this one up here. So looking at it in function notation, it's actually going to be 3 times f of x. So it's an a value of 3. So this is a vertical stretch. I never see anybody say expansion there, but that's certainly not wrong. If you say it's a vertical expansion, that's just fine. It's a vertical stretch by a factor of 3. Replace y with 6y and x with 1/3 x. So let's write out what the function's going to look like first. If y is 6y, move it to the other side, it's going to be 1/6 on the other side. F of, and this one just goes in the way it looks, 1/3 of x. So, vertical compression by a factor of a 1/6. And then from this inside, this is actually going to be an expansion then, because it's always by 1/b. So this is a horizontal expansion or horizontal stretch by a factor of 3, 1/b. So I know it's really kind of confusing which things are backwards. Everything keeps getting flipped around a lot. This is my main one. I like to see it in this form and go to this form. This is what you should start with for understanding it. The replacement notation I would worry about after. But make sure if you see it in this form, the a is the right way. So you're multiplying it by a 1/6, so it actually is shrinking. And the b value is always backwards. Everything inside the function is always backwards. So 1/3 means you're actually multiplying it by 3. So it's actually expanding. So backwards inside, right way on the outside. Okay, very last question. The graph is shown. Sketch the graph of f of -2x. Interesting. So we're going to be doing two things. We're going to be taking all of our x values and we're going to be multiplying them all by -1/2. Right? Nothing actually happens to the negative. There's no backwards for the negative. So we're actually going to be shrinking all of our x values by a factor of -1/2. Everything gets kind of pulled in. Times, I should have just written it like this, -1/2 x is what we're going to be changing them to. So we need to find all these new points. This one is the one that stays the same. I actually always start with my anchor points. So for x transformations, the y-axis stays the exact same. Next two, so this is 6, so it becomes 3, it becomes -6, so it becomes -3, becomes +3. 1, 2, 3. That's where that one goes. This is 4, so it becomes positive 2. 1, 2, and the same height. The height's not changing, only the x values are changing. This one is 1, 2, 3, 4, so it becomes negative 2 at the exact same height. This guy is 5, so it becomes 2.5. 1, 2.5. And this is 6, so it becomes 3. So very steep at the end there. And then you just have to connect the dots. No arrows for this one, because this one has actual endpoints. And that's pretty much all we're doing for that. Okay, homework questions. I'm not sure if we'll do the other half of the lesson today. If you finish the homework fast enough, maybe we'll try it.